So now let's talk about a new topic called a functional principal component analysis. This is one of the most important topics in functional data analysis. It's used a lot in functional data analysis. So really, I will see this is probably the fundamental skills we used when we do the functional data analysis. So today we will learn some these basic ideas for the functional principal component analysis. So basically, before we focus on individual curves, right? We focus on how can we transform some discrete measurements on the curve to a continuous function, right? So we only focus on individual curve. But in functional data analysis, the idea is we will treat each curve as one observation, right? So in other words, in functional data, we will analyze multiple curves, right? So when we have multiple curves, and we need to have some summary statistics. So the summary statistics we can use is we can using the mean curve, right? So basically, is the pointwise average along of all these curves at each time point, right? So this is the mean curve, and also we can look at the covariance function. So this is the definition: sigma st is a covariance function among this curve. Basically, it considers the covariance of xi at the time s and the value of xi at the time t, right? Okay, so here this is this bottom of this slides show you two graphs. On the left side is show the temperature, the mean daily temperature in 35 Canadian cities. Okay, so the red one here is the mean curve of this temperature curve. Okay, so yeah, and the right panel is to show the covariance function of this functional data, and so we cannot see much thing here. I find when we look at the correlation of all these functional data, I find the correlation is more helpful. Okay, so this is the definition for the correlation of functional data. So the correlation for this temperature curve is put on the right panel, and so you can see here. So this is the contour plots. Okay, so basically you can see here. So this is the correlation of the temperature curve at the time t with the temperature curve at the time s. So the x-axis is basically the t time point, and the y-axis is the s time points. So not surprisingly, in the diagonal part, they are the correlation with the in the same time. So the correlation equal to 1. And off the diagonal, you can see here, interestingly, because this temperature is a periodic function, right? So in other words, the correlation at day 1 will be very correlated with the day 365 because they are both in the winter, right? So therefore, you can see here, basically in this orthogonal, along with the diagonal part, this diagonal part, the correlation is also very big. This is not surprising, right? And also the lower correlation is when basically we look at the correlation with the temperature data in the summer with the winter, right? So the correlation is the smallest, but yeah, it's around 0.45. Okay, so this is a correlation with functional data. So we can see something from this temperature data because the temperature curve is still pretty simple, right? Basically, it's almost like a quadratic curve, right? But if you look at more complicated functional data, like here for these examples, this to show the in our first functional data lectures, this is the position of the when we write FDA, the change of the pain along in the paper, and so you see here on this movements is more complicated, and in this case, if we look at the covariance surface, it will be much more complicated, right? We can see nothing here. Okay, so a fundamental problem when we're dealing with these multiple curves or these group of curves is that we want to find out in which time point we have the maximum variations, right? So, for example, if we just look at this handwriting data, and so just look at this by eyes, we can see here basically in all these peaks or the valleys, the variation is the largest, right? Just look at it vertically, okay? But we need to have some way to quantitatively to provide to describe these major variations. So what can we do? So so back to the multivariate statistics. So when we have multiple variables, so we have the principal component analysis to define the direction of the largest variations. So for example here, this is give you one demonstrations. Like suppose here we have two variables, x1 and x2, and each circle represents one individual observations. And so if you look at it here, you will find out that in this solid red line direction, these circles has the largest variations, right? Okay, so then we will pick this direction as our first principal components because in this direction, it has the largest variations. Okay, so in that case, we can project all these two-dimensional data on these one-dimensional functional principal component lines. Okay, so in that case, two dimension of this data become one dimension. Okay, so this is the dimension reduction techniques. And you can see here, when we project these circles on this first FPC, the first principal component, it has the largest variations in these projected points. Okay, so this is the ideas for this principal component analysis. So, more details about this math behind the function behind the principal component analysis is that actually we are using Argand decomposition, right? So suppose here we have this x is a vector of these multiple variables, and we can find the covariance matrix for this x, and so then we can find out the projection of x on the direction u. Suppose u is the principal component. So then the projection of x on the direction u will be u transpose times x, right? So this is the projection of x on the direction u. So in this projection is also called PC scores, right? So we can find the variation of these PC scores as equal to u transpose times covariance matrix capital sigma times u. Okay, so now what we're trying to do is to try to find out the maximum the direction where the projected PC scores has the maximum variations. So therefore, we want to maximize this variance of these projection scores, U transpose times sigma times U. Okay. At the same time, we want to make sure the U is identifiable. These principal components. So you may find out that if we get a U maximize this quadratic form, we can always multiply this U by 10, for example, right? Then this quadratic form will become 100 larger, right? So therefore, we only care about the direction of the U. Therefore, we will put the constraints that the length of the U has to be equal to 1. Okay, the length of the U means U transpose times U equal to 1. Okay, so with these constraints, we want to find out the U that maximize U transpose times sigma times U. So this is the constraints optimization problems, and it is hard to do this optimization directly. Unfortunately, in linear algebra, we already know that the U maximize this quadratic form U transpose sigma U actually is the eigenvectors of capital sigma. Okay, so therefore we only need to find the eigenvector of capital sigma. We were able to find out the FPC, the principal component U here. Okay, so basically we will solve eigenequations. So eigenequations is capital sigma times U equal to lambda times U. Okay, so U will be the eigenvector of sigma, and lambda will be the eigenvalue of capital sigma. So this is the basic math behind the principal component analysis. Okay, how many of you have learned principal component analysis before? Can you raise your hand? Okay, so most. Okay, yes. Okay, so now we have knowing this principal component. So now let's look at there's some more background of the principal component analysis. So when we estimate the principal component, basically first we will estimate this covariance matrix capital sigma. So here X is actually the vector. Okay, so this is the definition of the sample estimation for the covariance matrix, and then we can take the eigendecomposition of sigma. So sigma equal to U transpose times D times U, and so here the U, the column of the U will be orthogonal to each other. Okay, and also basically each column of the U will be the principal components, and for the D, it will be a diagonal matrix, and so each entry in the diagonal will be the eigenvalue of the capital sigma. So we call this as small d times k, and so you can calculate that dk actually is equal to the variance of the PC scores. Okay, so therefore we will order this dk by in the decreasing order, and so here the case column of the U will be the UK, and it is the case principal component. Okay, and also we can look at the ratio of dk over the summation of all the dk's. We will call this as a proportion of variance is planned. Okay, so the principal component scores will be xi minus x bar transpose times the UK is the principal component score. Okay, so this is the some introduction for the principal component analysis, and you will find out we will have a functional version for this PCA, and it's very close to this principal component analysis, actually. So, as I mentioned, functional principal component analysis actually plays a crucial role in functional data analysis, and so in many functional data analysis methodologies, they are based on functional principal component analysis. Okay, so basically here is that for FPCA, we want to find the top k functional principal component. So here I noted as W1 of t to W sub k of t. Okay, so these top functional principal components summarize the major source of variations among these multiple curves xit. Okay, and then here I want to mention that this xit, I assume that they are centered curve. In other words, the mean of xit, I assume here is equal to 0. Okay, just to be make it simple, because here when we do the FPCA, we mainly focus on the variance of the curves. So we will always first remove the mean curve. Okay, so for this xit, basically after we get this top k FPCs, we will project xit to the FPC score. So FPC score will be s sub I1 to s sub ik. So basically this curve xit can be written as a linear combination of this FPC wkt, and this s sub ik is the coefficient to this k FPC. So you may realize that this is very similar as when we talk about basis expansion, right? So in the first lectures, we talk about how can we use B-splines or Fourier basis functions to represent one curve, right? And here, this wkt will be a new basis function to represent this curve xit, okay? And so we also actually, in the summary of first lectures, we mentioned that there's also called empirical basis functions. Actually, this wkt will be the empirical basis functions. So these basis functions actually will be estimated directly from the data, okay? So the benefit to using this wkt here is that before, when we do the B-splines or using the Fourier basis functions, so they are general basis functions working for all curves, right? So in order to working for all the curves, we generally will have to make put many basis functions, right? So so if we have 100 time points, maybe we can put 100 basis functions. And so the advantage when we using this empirical basis function wkt here is that actually we only have a very small number of basis functions. So in most cases, this number will just be equal to 3 or 4, okay? The number of principal components, okay? It will explain the most variations in the data. So therefore, so this can be like a huge dimension reduction for this xit, because xit is an infinite dimensional function, right? Basically now we project this infinite dimensional curve to this finite FPC scores, like 3 or 4 scores, to represent so basically we project the data from infinite dimension to 4-dimensional, right? So that we have a big dimension reduction here. Okay, so yeah, so for most of these top FPCs, actually the shape of these top FPCs are generally pretty simple, and we will talk about how can we interpret the FPCs in our following lectures. So when we estimate the FPCs, basically we will estimate these FPCs by some flexible basic functions like using B-splines. Okay. So here is one example. So this functional data I show you in this graph. Basically, to show the number of eggs laid by 50 Mediterranean fruit flies over 25 days. Okay. So our objective is to try to explore the major modes of variability in these 50 curves. Okay. Before I'm going further, so if you look at this data just by eyes, can you find out in which age, in which time this curve have most variations? If you look at this data directly. Any ideas? Joe, so if you think like the early age or the later age has the most variation in these curves?
Well, certainly a larger range in the earlier.
The earlier, right? Yes, definitely. You can see here we have larger variations in the early age than in the later age, right? Okay. Yes. Okay. So later on we will learn how we can use the principal components to quantitatively to describe these major mode of variations. So now let's go into some details for this functional principal component analysis. So here, suppose we have n curves, okay, using x1 star t to xn star t, okay. So after we get these curves, we will first do a pre-processing. So basically, we will first get rid of the mean of the curve, okay. So we have this mean curve mu of t. So we will do the pre-processing, and we will remove the mean curve from each curve, and I put this center curve as xi of t. So for FPCA, we always will working on the center curve. So basically here, I denote the first FPC equal to W1 of t. And so after we get the W1 of t, we can calculate the score to the FPC, first FPC, as the integral of W1 of t times xi of t dt. Okay, this will denote as S sub I1. Okay, so basically you can understand that in the functional space, this integral actually is the inner product of W1t and xi of t, right? So this is the first FPC score. So now the objective is that we want to try to maximize the variance of this first FPC score xi S sub I1, okay? Because here these curves are centered, therefore this FPC score S sub I1 is also centered. So therefore the sample variance is just the summation of squared of this FPC score, right? So here the idea is we want to maximize this variance, the summation square of this FPC score, S sub I1. And here, as we mentioned that we can always multiply W1t by 10, and this variance will become 100 times larger. So therefore, we will always put the constraints that the integral of square of W1t equal to 1. Okay, so this is, we have these constraints. So so here this W1t represents the strongest and the most important mode of variation in these n curves. So, and now let's look at the second FPCs. Let's denote this as a W2 of t. Okay, so the score to the second FPC W2 of t will be S sub I2. So this will be the inner product of W2 of t and Xi of t. So here we try to maximize the variance of this second FPC scores. So again, this second FPC score has the mean equal to 0. Therefore, the variance is just equal to the summation of the square of this S sub I2. And again, here we will put the constraints that the length of this second FPC equal to 1. And also, we want this second FPC to be orthogonal to the first FPC. Therefore, we will have the constraints that the inner product of W2t and W1t equal to 0. Means that W1t and W2t are orthogonal to each other. Okay, so this is for the second FPC. So we have one more constraint. So W2t represents the second strongest and the most important mode of variation in these n curves. Similarly, we can obtain the rest top k FPCs W3t to Wk of t with this similar way. Okay, and we want to make sure that all these FPCs are orthogonal to each other. Any questions? Yes?
So in the beginning, you were saying you were projecting the data of infinite many dimensions onto a finite space. So could you explain how the original space is infinite dimension?
Why the original space is infinite dimension? This is a very good question. The reason is because the original space is basically is Xi of t, right? So it is this n curves, okay? And this Xi of t is a function. So the function is infinite dimensional.
In terms of t?
Yes, in terms of t. That's right. Yes. Yeah. Yeah. So here I also want to mention that another difference between multivariate PCA and functional PCA is that for this functional FPCA, there's actually only one variable if you think about it, right? So for example, this is like this X curve, right? Just one variable, just measured over multiple time points, right? So in other words, when we work on multivariate PCA, actually we have multiple variables, right? Okay, so this is the one difference between functional PCA and multivariate PCA. So for functional PCA, we actually only work on one variable. The second thing is that so if you look at the connection between functional PCA and functional and multivariate PCA, is that if you look at the value of xit at any time point, right? So we have, for example, for this x curve, we have the value of x1t at time 1, time 2, time 3, time 4, right? If you look at the value of xit at each time point at one variable, then we will have multiple variables, right? Yes. So this is the connection of functional PCA with multivariate PCA. Okay. If you treated the value of the curve at each time point at one variable, then you will have multiple variables. Okay. So this is kind of more connections with multivariate PCA. Yes. Brenda.
I was just going to ask, like, let's just say, you have functional data, but instead of having curves, you have surfaces. So you have like multiple variables measured at a particular time point.
Yeah.
Then would you apply both types of PCAs, like one for each time point, where you would do the regular multivariate PCA, and I guess take the two variables you measured and project it onto a single dimension, and then then you do FPCA over time, right?
So you are talking about, suppose we have multiple functional variables.
Yes.
Like we have temperature and the temperature curve and the precipitation curves.
Yeah.
How can we do that, right?
Yeah.
Okay. Yes, those are very good questions. Yeah. So in that case, there actually we have a multivariate version for this FPCA. You can do that. Yes. Yeah. We will introduce this in our next lecture. Yes. Yeah. Okay. Good question. Any other questions? Okay. So here, this is just before we going through the detail how to get the FPCs. I first want to talk about how to what this FPC will look like. Okay. So here, this is to show you the top two FPCs for the medfly data. Okay, for the curve I showed you in the beginning. Okay, the number of eggs laid by this medfly. Okay. So you can see this is the left panel show the first FPC, the W1 of T, and the second panel to show the second FPC is W2 of T. Okay. So both these FPCs are estimated as a linear combination of B-spline basic functions, and so these two curves explain the 91.6% of total variations of the data. Okay. So you can see just the two FPCs, they can explain the large proportion of total variation in the data. And also you can see for the medfly data, actually it's pretty messy, but if you look at the FPC, actually it's very simple, right? Yes, it's just these two simple curves with simple trend. Okay. So let's look at it more closely, and I find out one big problem or when we work on FPCA is that how can we interpret the FPC? Okay, that's kind of big problem when we work on the interpretations. So let's look at this together. Okay, so here let's look at it before we go in. So this is the first FPC. I plot this here again, and let's look at the formula for the FPC score. So the FPC score S sub I1 equal to the integral of W1T times Xi of T dt, right? Okay. So you can find out this first FPC is planned around 62% of total variability. I will explain later how we can calculate the 62%. Okay. So this first FPC, if you look at it closely, you can see here the y-axis. Actually, all this first LPC is positive over the whole time interval, right? So there's no negative value for the first LPC. And if you look at the definition of the first LPC score, S sub I1, this is the integral of W1T times Xi of T. So in other words, you can treat the W1 of T as the FPC score as the weighted average of Xi of T along the whole time interval. Okay, and this FPC W1 of T serve as the weight on the average, right? So in other words, the first FPC score is the weighted average of this Xi of T, right? So we will put more weight around day 9, right? And less weight in the later stage, right? Okay. So therefore, we can interpret the first FPC score as the weighted average of the number of eggs laid by 50 fruit flies over 25 days, right? So this is the interpretation for the first FPC scores. Okay. So surprisingly, you will later find out that we have tried many examples. Surprisingly, the most first FPCs will have the similar shape. Okay, it will be positive over the whole time interval. Therefore, for most cases, the first FPC score can be interpreted as the weighted average of the curve. Okay, yes. And now let's look at the second FPC. So the second FPC is this shape, and so this is the formula for the second FPC scores. So S sub I2 equal to the integral of W2 of t times Xi of t. And this second FPC explained around 29% of total variability. And so you can see here, this part is wrong. Okay, actually the second FPC is negative before day 8, right? And then become positive after day 8, right? So again, here, the second FPC scores is also the weighted average on this curve XIT. The difference here is that the W2 of t is negative before day 8 and positive after day 8. In other words, this FPC score basically is the weighted average of this curve after day 5 minus the weighted average of the curve before day 8, right? Because there's a negative weight before day 8 and a positive weight after day 8. Can you see it? Yes. So if you think about this integral, basically you can put this as the pointwise average of W1 of t, right? Yes. So so the weight before day 8 will be always negative, will be minus, right? So the weight after the day 8 will be always positive, right? So therefore, the second FPC can be interpreted as the change of the number of eggs laid by the fruit flies after 8 days compared to before 8 days. Okay, if we have the most change, the FPC score will be larger. Okay, so this is how you interpret the second FPC. Okay, and actually we found out that for most applications, the second FPC will always be positive in some interval and negative in the other intervals. So in most applications, the second FPC can be interpreted as the change of the process over 2 time intervals. Okay, so this is how we interpret the second FPC. Okay, is this clear? Okay, yes. Okay, yes. So I found out. I personally think it is easier to understand a second FPC when you treat this second FPC or the first FPC as the weight on the average of the curve. Okay, yes. Okay, so this is the interpreting for the second FPC. So now let's look at any questions in terms of the interpretations. Is this clear? Okay. So after we know how to interpret the FPC, so now let's learn how can we estimate this FPC. So you will see here, it's very similar to the regular PCA. It's also based on eigenvalue decomposition. Okay, so basically for the regular multivariate PCA, we were working on the covariance matrix capital sigma, right? So we were doing the eigenvalue decomposition on the capital sigma, right? And we will find out the eigenvector Ui, right? The Ui will be the PC, principal components, and the Di will be the eigenvalues of capital sigma, and Di actually will be the variance of PC scores. Okay, yes. So for the function PCAs, we were working on the functional covariance function sigma s of t, right? So we have the definition of sigma s of t in the beginning of our lecture. So after we get these functional covariance functions, actually there's a famous KL decomposition on the sigma s of t. So you can write down the sigma s of t equal to the infinite summation of dj times wjs times wjt. Okay. So this wjt here will be the JS functional principal component. And the FPC score will be just the integral of wjt to the xi of t. And the eigenvalues dj will be the variance of the LPC score S sub ij. So here dj represents the amount of variation in the direction wj of t. Okay, so therefore we can use dj divided by the summation of all the dj as the proportion of variations is planned. Okay, any questions? Is this clear? Okay, yes. So this is so remember before we talk about the 62% or 29%. This is basically based on the this proportion dj over the summation of all the dj. Okay. Yes. So how can we compute LPCA? So basically we can compute LPCA by solve the eigenequations. So this is the functional version of the eigenequations. It's the integral of sigma s of t times wi of t dt equal to lambda times w1 wi of t. So sorry, here should be wis, okay, because t is integrated out. Okay, so there are two options. So one option is that you can take a fine grid from t1 to tk, and then you can evaluate this sigma s of t and this fine grid, and you can find a k by k covariance matrix, and then you can do the eigen decomposition, and you can find out the eigenvectors, and then you can do the smoothing on the eigenvectors. This is the first approach. Okay, generally we don't use this approach. So we often will use option 2. Okay, so basically because in the real application we never will know xi of t, right? So we only have the discrete measurements on the xi of t. So therefore we will always represent xi of t as a linear combination of the basic functions, right? Okay, so then we can impress these eigenequations based on this coefficient to the basis expansion. So now let me show you how can we do this. Okay, so suppose here this x of t is a vector of all the curves. Okay, so you can see here x are using bold font because I treat this as a vector of the function. Okay, so then x of t will be equal to c times phi of t. So basically the x of t is a n times 1 vector, right? And so phi of t is also a vector of all the basic functions. Suppose here we're using capital J basic functions, then phi of t will be j times 1 vector basic functions, and then this C will be all the coefficients to the basic functions. So the dimension of the C will be n times capital J, right? Yes. Okay, so if we have this representation, then the covariance function sigma s of t will be just equal to 1 over n xt transpose times x of t. Okay, so because these curves are all centered, so then this one can be written as this form. Basically, you replace 1 over n xt transpose times x of t by this basis expansion form. Okay, so this is the representation for sigma s of t, and then we can represent this weight function w of t as a linear combination of this same basis function. So we will use b as the coefficients for this FPC function w of t. Okay, so therefore wt equal to phi transpose t times b here. So here we want to maximize this. We want to solve these eigenequations, this form, right? So now with these constraints, the length of wt has to be equal to 1. So you can represent this length, the integral of square of wt, as this form, quadratic form, b transpose times this integral of phi t transpose times phi t dt times b equal to 1. So we will call this complicated multiplication of the basic function as the matrix W. Okay, so so I think here the transpose should be on the second phi of t here. Okay, as a typo here. So this W should be a J by J matrix. Okay. So after we got this, and we can want to maximize these eigenequations, right? So how can we do these eigenequations? So I can show you here. So